And it's like a marathon for me. And I know you're already tired of me, but please bear me with another 1.5 hours, okay? So I'm gonna spend the last 1.5 hours talk about the selected statistical methods for modeling, okay? So we go back to ODE. Good news is that Ray actually gave the talk and ended with saying that ODE can be used to model gene expression data. That is true, okay? So whatever I talked here actually will also be useful. The first thing I want to cover today is the confidence interval, okay? So before I actually go to the technical details, I would like to talk about talk a little bit about the model and data. So we know the goal that we use models and data is to figure out what's the system structure or what is the underlying mechanisms. And to do that, you usually need to solve the so-called inverse problem of ODE, which means you have to determine unknown parameter values from usually time course data for given model structure. So for simplicity, I use some notation here. What you saw here, this one is just the ODE model as we described yesterday and the day before yesterday. There's one more equation here. That's actually the model for the data. So yes, we can actually model data directly by add an error term, okay? So here h is a function of t, x, and theta, which means if I can solve this ODE equation, I can plug in x here. And also if I know the theta, I can also plug in theta here. Well, just because what you measured may not be just be the x itself, okay? You may measure a function of x. For example, you measure total of the T cells instead of measure the uninfected T cells and infected T cells separately, okay? So that's a very simple function, just the T plus T star here, okay? However, this is a general form, okay? What's important is here, okay? Epsilon. Epsilon here is a measurement error. It is a random variable. So it must follow certain distribution, although most of the time we don't know what the exact distribution is. Although we usually assume, okay, this distribution is normal if we have enough sample size. So usually we call this one like a mechanism model or mathematical model. We call this one data model, okay. So when we solve the inverse problem for ODE, there are some possible issues we need to consider. The first one is usually, like I just mentioned, okay, usually just some part of the state variables can be measured. And also, whatever data you get, they are subject to variations. For example, variation within subject, variation between subjects, or just a measurement error. So one example of the variation within subject is that if you measure the T cell number, okay, for the exact same subject, patient, you measure it in the morning or you measure it in the afternoon, that actually will make a big difference, okay? Example of the variation between subjects is that if I have two HIV patients, okay, of the same age, the same annual income, the same race, the same local area, okay, although given many common factors, okay, the measurement of the same variable, okay, in these two subjects will still be different, okay, and they can be actually very different, okay. So another thing I want to talk about is measurement error. The so-called measurement error can come from your instrument, okay, whatever technique assays you use, okay. You always comes with error, okay. For example, you take a small drop from the culture, then you count the cell number, and then you calculate the total cell number based on what you see, okay. That calculation actually come with actually error, okay. So data itself has errors, so that's why when we solve the inverse problem for ODE, okay, we need a counting rule. Basically, the counting rule can tell people how reliable your results are, okay? Or I can say it can quantify, okay, the uncertainty in the parameter estimate. So first I want to actually go over the basic idea of concept of counting rule. So counting rule itself actually is comprised of two random variables, okay? It's not just a single random variable, okay? It's two random variables. One is the lower bound, another is the upper bound, okay? So when we talk about the random counting rule, you have two, okay, values to determine. And also, this lower bound and upper bounds, they are expected to cover the true mean, okay, with some given probability, okay? Of course, you're saying that can we find some counting rule that cover the true mean with 100% probability? Yes, there is such a counting rule from negative infinity to positive infinity, but that's just trivial, okay? So what we usually do is that we give a significance level. That's actually also the type 1 error, okay? 0.05. So we're usually saying that this interval has a 95% chance to cover the true mean, okay? That's the meaning of the confidence interval. So to calculate confidence interval, the classical method is called the Fisher information matrix, okay? So here I don't want to talk too much about the technical details, okay? But anyway, let's just go through, okay, the basic steps, okay, how we derive this kind of, Fisher information matrix. So first, we have to make assumption about the distribution of the minimum error, okay? For simplicity, I just use the multivariate normal distribution, okay? If you are not familiar with the multivariate normal distribution, just think about this simple example. This is the normal distribution for one-dimensional variable, okay? When we talk about the multivariate normal distribution, which means the dimension should be 2 or greater, okay? And let's use a two-dimensional problem as an example. So in this case, the multivariate random variable, multivariate normal distribution will look like this, okay? It's still a bell shape, but in three-dimensional, okay, space. So if I draw the contour on the surface, okay, it's more like a height, okay. So it's symmetric around this axis, okay. So that will be so-called multivariate normal distribution. And if I write this multivariate normal distribution in terms of mathematical expressions, okay, MVN here actually denotes multivariate normal distribution. And the mean of this distribution is 0. And sigma 2v here is actually the covariance matrix, okay. And don't bother to figure out why I write the covariance matrix in this way, okay. Actually, it's just for the computing convenience. But let's just say this term is the covariance matrix. Okay, that's all. So now recall that if we use least squares to estimate parameters, okay, we can actually, this is actually our objective function, okay. For now, again, ignore v here, okay. This is just a general form, okay, of the least squares. However, I probably need to spend a little bit of time to explain, okay. So here I write this object function in a vector form, okay. So y here is actually a vector. It's not a single value. It's actually y1, y2, yn. Okay, and h here is also actually a vector. So y minus h, that's the difference between two vectors. It's actually equal to okay. So when I multiply the transform of this vector with another vector, which means the transform actually just lay down, okay, this vector. So from a column, it becomes a row. That's what it means, okay.
Do you assume that the y vector and the h vector have the same number of elements?
Oh yeah, they should.
They should, okay.
Right, remember? So once you have a y, you have y h. There's an equation there, right?
Oh, yeah,
Right. So that's a data model. Now, if I multiply this with multiply a row with a column, okay, what I do is that y1 minus h1, okay. I multiply this one with this, and then add the product of this one with the second term here. So eventually, you will get actually so that's our least square, okay? That's what we actually talked about before. Now I just right now I just write it in a vector form, okay? So they're the same thing. So now we want to minimize this object function, right? And remember, actually one of the students actually asked the question. Remember, at these places, that's actually all the local minima or maxima, okay? The slope is 0, right? So now, since we are trying to minimize this function, so the solution to this minimization problem should also has a 0 slope, right? That's why we start from here. So this is the slope respect to theta, the parameter, and now it's become 0. That's where our solution, okay, is. So start from here, we can actually plug in this expression and then do some, operation. Okay, you get this form, and later you will find this form actually useful to to determine the distribution, okay, of the difference between the estimate and the true parameter value, okay. So what we expect is that our estimate is unbiased estimate of the true parameter value, right? Which means we want if the sample size is large enough, we want our estimate become exactly the same as the true parameter value, okay? However, so due to noise or whatever reason, you may have a difference, okay? And this difference itself is a random variable. So this random variable actually follows the distribution like this. And actually, that's what we derived based on what we derived in the previous slide, okay? So now, this distribution has a mean 0, and this is the whole term is a covariance matrix, okay? And if you look at this part, that's what people call the Fisher information matrix, okay? So now we know, if we know the Fisher information matrix, we can plug this in here. Then we can actually calculate the variance, right? Then we get the variance of the estimator. And we know the variance of the estimator, then we can get the constant rule, right? There's a relationship between the, for example, if you calculate sample mean, okay? You calculate sample mean, that's a mu plus minus 1.96 standard error. Familiar with this one? The standard error, the square of standard error is what? Is the variance, right? So that's why, okay, Fisher information matrix can be used, okay, actually is defined to calculate the constant rule. So now we sort of know how to derive the Fisher information matrix. However, now I want to actually think about what will be the problem you can tell right now for Fission information matrix. If we look at the expression here, the first thing you will see H itself, okay, because we have been talking about most of the ODE models, okay, in practice cannot be do not have a closed form solution, right? You have to solve it numerically. So H is a function of X, so H has also to be numerically calculated. Once you numerically calculate something, it will have zero. Okay, there's numerical error. Now you take the derivative of numerically calculated number with respect to theta. You, for example, using the approximation we talked about, okay, finite difference approximation. Then you actually introduce more numerical error, okay? So that's why sometimes the Fisher information matrix will become singular. Become singular, which means you will not get a solution. The computer program will return something like this, okay, to you, not a number. You will not get a finite number or for your results. If you get a non-number, that's probably it, okay, because the Fisher information becomes singular. So the other problem is that sometimes the Fisher information matrix can be very, very conservative. Conservative means, for example, if I estimate one parameter, okay, and the parameter estimate is 1.0, and now if I use Fisher information matrix to calculate the confidence interval, I get 0.99 and 1.001. It looks too good to be true, okay? Especially when you have a noisy data set, okay? You're not expecting to get a narrow confidence interval like this, okay? But for cases, okay, when I actually use the Fisher information matrix for many ODE models, I frequently get this kind of thing, okay? That's it's conservative. That's one reason. Another reason actually is the numerical error. Okay, so later actually when I modify my code, I find out that when I use numerical approximation to calculate this derivative, okay, if I change delta theta, sometimes I can get whatever I want, okay, from this kind of result to this kind of result. So which means sometimes the numerical error totally destroyed your result. And by manipulating this parameter, the interval, okay, you can get whatever you want. That's cheating, okay. So that's one reason when I publish something, I usually avoid to use this Fisher information matrix for ODE model, especially for a nonlinear ODE model with noisy data set. Okay. So what will be the remedy? So we talk about lots of bad things about it. So we must have some solution, right? So that's why actually I want to talk about Bootstrap method, okay? Bootstrap method, you can define it as a simulation estimation method for finding confidence interval. I will explain, okay, what I mean by simulation estimation, okay? This is not actually a rigorous definition, okay? Just for, you know, for easy to understand, okay? The basic idea here is that we approximate the unknown distribution of the difference, okay? Remember? This one is the random variable, okay? You approximate the distribution of this random variable by resampling either the data or the residuals or weights. I can explain, okay, each term or later. So in general, okay, Bootstrap method can be non-parametric or parametric. nonparametric, which means we do not make assumption about this distribution. For example, I'm not assuming this distribution is normal. Okay, when I say it's a parametric bootstrap, I will say I assume this distribution is normal, whatever, or gamma. So it's like we do the t-test, okay, or the nonparametric test. If we assume the data follows a normal distribution, we actually are doing parametric test. If we're not assume the distribution of the data, we're doing nonparametric test. That's the same thing here, okay. So now let's first look at the classical, okay, nonparametric bootstrap. Let me go over the basic steps first. Then I will actually give you an example. Okay, if you don't understand when I talk about the steps, that's fine. Okay, for now. So first we're gonna compute the estimate from the real data set y1 to yn. Okay, so theta hat here is the estimate from the real data set. Now I draw a sample y1i, y2i, up to yni of size n with replacement from the original data. And then I compute the estimate theta hat I for the ith sample. And I repeat it, for example, 1,000 times. Now I get 1,000 estimates, right? Then we sort all the estimates I got. And then if I use 0.05 as the significance level, then the 26th and then 975th parameter estimate will be the lower and upper bound, respectively. So implementation-wise, it's simple, right? You just sort them and from smallest to largest, and then count a number, okay? And why I start from here and end here? Because I have 1,000 estimate, and this error rate is 0.05. 1,000 multiplied 0.05 is equal to 50. So I spend 25 at the bottom, spend another 25 at the another end. Okay, that's why I split the. I can get this error rate. Okay, that's a simple math. Okay, you can do. So if you're also interested in, now I already get my constant rule. Okay, if you also want to report your standard deviation, okay, this is what you can do. Okay, just a sample standard deviation. So now let's actually look at an example. Okay, so
how do you choose the size of n?
That size of n should be equal to the size of the real data. Okay, if you have 10 observation in your real data, then you have to just 10 data. Okay, when you resample the data. Okay, so let's look at an example. Okay, that should be much easier to understand. So let's say this is my real data set. This is my real data set, okay? And now, of course, based on this data, I will fit the model to get my parameter estimate, right? That's first step. Second step, I want to draw a sample from this real data set. So remember, we have a time course data, okay? So this is at T1. Okay, this is the value we observed at T1. This is at T2, T3, T4, T5, T6, right? Now when I resample it, okay, I'm gonna just shuffle them, okay? The first sample I will get, for example, 1.3. So first thing I want to mention is that, see now, I sampled this data point twice because that's a sample with replacement, which means after I sample the number, I put it back. then next time when I sample it, I still have a chance to sample the same number. That's why you see this. Second thing I want to mention is that now my time points, okay, the position of the time points are still the same. However, the value at each time points change. So we basically change the pattern of the data, okay, by doing the resampling. This is actual data. Yep. This is called the resampling data. The residual thing, that's the second thing I'm going to talk about. And also, you can actually generate weight. Okay. So there are three different Bootstrap methods you can use.
How could I take a viral titer time point from day 2 or 3, which might be near the peak viral titer, and put it in?
I understand this. The basic rationale, okay, is this actually. If I get no response, my parameter value should be 0, okay? Then my system output will be a flat line, right? And then my data will be all on a horizontal line, okay? So in this case, doesn't matter how I, change the position of the data points, I will still get a flat line, right? And that's the basic rationale. If it's not, then you change the order of the data should have a consequence. Okay, that's the basic idea here. So now I can draw another sample, right? So I can keep doing this for 1,000 times. Okay, then for each, I will get a parameter estimate. So now what we did actually is to generate a sample from the distribution of theta hat. That's what we do. Okay, we generate a large sample. Okay, 1,000 observations. We generate a sample. So now, since we can just use the empirical distribution, okay, to calculate the constant rule. That's why I just count the number, sort them, and then count the number. Okay, then use it as a constant rule. Okay. So actually, this kind of classical Bootstrap method, okay, sometimes, okay, will give you an extremely wide constant rule, okay. You may not like it because when you report your results, okay, people are saying, I say constant rule cross 0. Okay, when your constant rule covers 0, which means statistically your parameter estimate is not significant. Okay, because 0 could be one of the true mean, which means your estimate statistically, okay, your estimate has no difference from 0. Okay, that's why people don't like it. Okay, if you get a -100 for theta hat equals to 10. Oh, probably I should take the middle one here. Okay. I get in trouble. Okay. So that's why actually, if you want to go a little bit, I should not say this because the problem, as Catherine just mentioned, by resampling data, you totally change the data pattern. Okay. If you totally change the data pattern, you are actually expected to get a wide constant rule. Okay. And sometimes I also think this is probably not so reasonable. Okay. So let's sample the residual. Okay. That's why we have the variations. Okay, of the Bootstrap method. So here what we do is that let's say this is a true curve, okay? Means there's no noise. Let's say it's a true curve, there's no noise. And here's my data. So now, for simplicity, okay, let me use the notation, okay, y1, y2, 2, 3, 4, 5, 6, 7, 8. This is my data, okay, y1 to y8. I have 8 points, data points here. And so my residual, this is a true curve or the fitted curve. If our estimate is unbiased, okay, the fitted curve should overlap the true curve, okay. So after you do model fitting, you will get a fitted curve and with the data points, right? And assume your fitted curve overlap with the true curve. Now we can calculate the residual. Residual actually is the difference from the data points to the fitted curve. It's called R1. R2, R3, and so on. Okay, so we have R1, R2, R8. So now, next thing we want to do, I want to resample this residual. So by that I mean I randomly shuffle them. Okay, I randomly shuffle them. For example, I can get this is still with replacement, okay. So now I actually, since I'm not resample the data, I'm resample the residual, okay. So I get let's call it R1, okay. This is our first set of sample of the residuals, okay. Create R1. You can also do the same thing, okay. Create R2 and R1000. Now, what I'm gonna do is that I add these reshuffled residuals back to the fitted curve. Then I generate a new data set. That's how it works. So eventually, I will still generate a simulated data set. So I add this back. That's H plus R1. That's my first data set. Simulated data set. This one, I will get H plus R2. That's another data set. Basically, I mean, I move this residual around. Okay, I create a new data set. This is H plus R1000. For each of them, I fitted the model, again, like we did before. Here I get the theta height 1. Here I get the theta height 2. Here I get the theta height 1000. Okay, what's left is the same. Okay, sort them, count the number, you get constant row. That's it. Question? Okay, so there's one more trick you can do, okay? So the third Bootstrap method, I will not sample the data. I will not sample the residuals, okay? I actually just generate random weights, okay? For each data point, I generate the weight. Okay. So this weight, they are random numbers that follows a distribution with mean 1 and variance 1. Now my least squares becomes this. Okay. So instead of just the square term, I put a weight in front of the squares. So for each data point, I have a weight. Okay, so that's called this one is another way to do the bootstrap. It's called weighted bootstrap. So same thing. You generate 1,000 sets of weights. Okay, W1I, W2I, W8I. And I is equal to 1 to 1,000. And for each of this object function, you get an estimate theta hat I. So what's left is the same. Okay. Oh, okay. I forgot to mention one thing. Okay, when I talk about the first classical bootstrap method, there is also an alternative way to do that. But this one is clear? Okay, the weighted bootstrap question?
So for the weighted one, you pick weights for each of the points before you do the bootstrap, and you just redistribute the weights, or you pick different weights every time?
Actually, you can do this. Generate 1,000 sets of weights first. And then, for each set of weight, you use it in a model fitting. Okay. Then you will not change the weight, okay, when you optimize this function. Okay. The weight has to be fixed before you optimize this one. So, is that clear? So, forgot to mention one thing, okay. The classical bootstrap method, there is also a variation, okay. Sometimes people don't change the order, okay. Some people don't change the order of the data, okay. They just sample the data, and if we happen to leave some data points out, that's okay. So this is also a typical way to do the bootstrap. So instead of
another one of the values, or just take one away?
Yeah, just leave one out, sort of like that. You probably, because out of the 8 data points, you may sample 6 of them, okay? Because that's with replacement, okay? So you probably sample this point 3 times. So you failed to sample these 2 points, okay? That's also a way to generate that. That constraint will be actually much more conservative, okay? So that's also one of the implementation you can do. So the first way I introduced actually is more like a permutation, okay, test. So now, since we talked about so many different bootstrap method, so however, I used all of it, and sometimes I will get reasonable results by using one method. By mean reasonable, because even I use bootstrap, sometimes I still get this problem. My estimate is 50. After I use bootstrap, my constant rule actually is so the estimate is not covered by the bootstrap, which means there are some distribution problem there. Where suppose, although we know use bootstrap, we can account for the skewness of the distribution. However, sometimes you still get this problem. That just means sometimes the distribution of this parameter is highly skewed. Okay, so it cannot be covered. So that's why sometimes I need to try a different bootstrap method. And the one method sometimes actually can cover it. So because it's based on large sample property, okay, which also means I may not generate enough sample or whatever, but doesn't matter, okay. So because you have very limited, I have very limited computing, not very limited computing resources, I cannot actually generate the 10,000, okay, samples. Actually, usually, if you do 500 or 1,000 samples, that's already lots of computing, okay, you need to do. So if this doesn't work, switch, okay, between the three methods I mentioned. Is that okay? So Bootstrap also, as you can tell, we didn't actually approximate the derivative, right? That's why most of the time it's robust and conservative. And however, I have to mention, okay, Bootstrap is very slow. You have to fit the model 1,000 times. Imagine that you are using the DSQP algorithm I showed you yesterday, okay? It's already slow, okay? You repeat this kind of thing 1,000 times. Sometimes I have to wait 2 weeks to just get a constant rule, okay? So after I tired of waiting, I actually parallelized the code, use OpenMP. Now, if you know how to code in OpenMP, whatever, similar things, actually you can finish this kind of thing like in a few hours. Then that's much more acceptable, right? So we hope that we have this parallel version of Bootstrap in Discover in the future, okay? Right now we have the Fisher information matrix. So if you get any trouble with the constant rule, okay, that's just because of Fisher information matrix, okay? So now I want to talk about the model-based experiment design. So today we have many statisticians, including me, okay? We'll talk about the, oh, by the way, I do have a statistician degree, okay? So we talk about we should, modelers, statisticians should kick in at the beginning of the study. So here I just want to show you an example, okay, how we kick in, okay? So first I want to mention something to you, okay? Even we collect many data points, okay, some data are more informative than others. Do you agree? So for dynamic system, okay, we observe, we collect the observations at multiple time points. And the observations at different time points have different information. For example, if you look at a steady state, if my system, of course, it's not look like steady state, but let's pretend it's a steady state, okay. At a steady state, if we want to determine this steady state, how many points we need? 2. 2, right? It's a flat line. You just need 2 points to determine the slope. If it's not a steady state, for example, if it's corner, okay, here, how many points do you need? As many as possible, because the slope are changing, keep changing, right? If you really want to determine all the slope exactly, you need as many points as possible. So that actually tells us, okay, in different regions, okay, the data has a different amount of information. So usually what we carry is this kind of thing, right? Because we can just put less data points here and put more data points here, if we know that how the dynamic system behave, right? So now, if I give you this example, and I have equally spaced observation. So if you have the choice, okay, to reposition these observations, what do you want to do? This one looks straight line to me, right? I probably don't need to, if I don't have minimum error, of course, here. I probably just need 2 points. That will be enough. And I will move these 2 points to the corner. Okay. So move this to probably here. So that will be something we can do and by model-based experiment design, which means we plug in parameter values. Before we collect data, we can actually get some, prior information from literature, right? For example, what's the possible value of theta? Plug in this into your model, generate the trajectory, and then you see the peaks and nadirs. Then you can actually start to make some suggestion. Okay. Should I put more observation here? That's kind of thing. Okay. That's the position of the data points. The other thing is that the number of replicates. I know usually when people design experiments, 3 mice, that's all. Okay, let's talk about 3 mice. Doesn't matter, okay. So in computer, we don't need to kill mice. So we can increase the number of replicates to say how many mice you need to kill, actually. Also, I don't like kill mice, okay. That's so in computer, I can increase the number of replicates from 3 to 6 to 9, right? And then we know if we have more replicates, we are supposed to get more reliable estimates, right? And this actually can be done in computer. Then you can find some acceptable sample size. For example, maybe we don't need to kill 9 mice to get a reliable parameter estimate. We'll probably just do 6. If 3 is okay, that's better, right? Save some money and also save some lives. Okay. So now I want to actually show you some example. Okay. We just talked about the basic ideas. Okay. And here, this one is called identifiability-based design. Actually, it's also based on model. Okay. Remember, when we do identifiability analysis, with the question we're trying to answer is that given the model structure, whether all the parameters can be uniquely determined, right? However, a byproduct of that kind of analysis is that we can also determine the minimum number of observations needed to determine the parameters. If under a condition that all the parameters are identifiable, then a byproduct of this is that we can tell actually what's the minimum number of time points we need. Okay. And of course, this case we ignore the minimum error. Okay. This one we haven't considered minimum error yet. We just talk about how many time points we need. So this model actually is a real model we actually use to model the rare fitness of HIV-1 virus. Okay. The virus, the wild type versus the mutants. Neglect the details of the structure, okay, for now. And what we do is that when we do the identifiability analysis, we formed this matrix. We formed this matrix. So after we check this matrix, if the rank of this matrix is 4, which means it's a 4 rank, then all the parameters are identifiable. And that's our conclusion. However, that's not the point here. Okay, the point here is that now, since actually I have a right-hand side. Okay, not just this is a rank equals to 4. Okay, originally I have a matrix at the left-hand side, and the right-hand side I have a vector. Okay, and this vector actually used the fourth order derivative of y. So we have y first order derivative of y. So how many data points we need to calculate the first order derivative? That's the rationale here, actually. That's why we can determine the number of observations. This one, remember, if we calculate first order derivative, we need 2 data points, right? This is slope. Calculate slope, you need 2 data points. That's y t plus delta t minus yt divided by delta t. These 2 different data points has to be different, okay? If they're the same, it's 0. Okay, so we need 2 points to calculate the first order derivative. So how many points we need to calculate the second order derivative? 3. Remember, we have a slide yesterday show you how to calculate the second order derivative, right? So you can calculate the derivative, second order derivative here. Same thing. First order derivative 2 points, second order derivative 3 points, then first order derivative you need 5. That's how we come up with 5 here. Okay, so at least you need 5 different data points, time points. Okay, that's so-called identifiability-based design, and unfortunately, there's no software packages available. For now, you have to do it by hand. Okay, sorry about that. So now let's talk about this one. Okay, the so-called simulation estimation sensitivity analysis. By calling it sensitivity analysis, actually, eventually, we'll go back to the experiment design. Okay, it's not actually, the purpose is not for the sensitivity analysis. Okay, eventually we're gonna just talk about the experiment design. So, this kind of method, we will not actually look at the changes in output as parameter value changes. Okay, what we look at is the effect of minimum error on parameter estimates. Okay, is a different type of sensitivity. Okay, how sensitive of our estimates are with respect to the minimum error? Okay, that's a question here. So, which means if I increase the minimum error from, for example, 20% of the mean to 40% of the mean, then what will be the change in the estimate? Okay, that's this kind of question. So which means I can tell at least you should get a 30%, control your minimum error under 30% of the mean. Then that makes sense, right? So which means sometimes you may generate low quality data. Okay, that's okay to do so if the model says, the simulation says okay. However, if the model parameters sometimes are very sensitive, then you may want to be careful, okay, and generate some high quality data. So that's also one of the issue if you write a grant proposal, okay, people ask you what's the sample size you want to use, okay. This is sort of the tool you can use. So the basic steps is simulation estimation, and then we calculate the so-called average relative error. The simulation means what? Means we generate simulated data from the model and parameter values, given parameter values. These given parameter values can come from the literature, okay, like what we did here, okay. So usually what we do is we have a model. Then we pull the value of parameters from literature. Okay, we sort of fix them. Okay, based on published work or previous study. Okay, then we solve it. Plug this in. We solve it. So we get the trajectory of x. After this, what I'm going to do is add a different level of noise. For example, I add 5% noise. This 5% is respect to this curve. Okay, I add 5% noise, then I add 10% noise, then I add 20 or 30. Okay, I add different level of noise by generating random numbers. Okay, actually this means you just generate random numbers. Okay, you generate random numbers, so your data will become. You will generate a simulated data set. Okay, then we fit each data set. We get estimate. Okay, for example, here for 5% noise level, we generate 100 data set. Then we get 100 estimate. Same thing. For this level, I also generate 100 data set. I get theta j. J is also equal to 1 to 100. This is I equals to 1. Okay. Clear? Do the same thing here. Now, for this one, for each level of noise, I can calculate the ARE. So what is ARE? Okay. We already get the value of theta, right? From literature, whatever. We treat that as a true value. Okay. So now, after I get my estimate, I'm gonna calculate the difference between the relative difference, okay, between my parameter, true parameter value, and my estimate, and multiply 100%. Since we have 100 data set, right? We get 100 estimate. Then we average them. So that tells us how far, in average, okay, how far our estimates are from the true value. Does that make sense? So in this way, we take account into the noise, right? Different level of noise. Right? So here is the example. We try a 0% error. This is just for validation. If you don't add any noise, you're supposed to get 0 ARE. Your ARE should be very close to 0, right? If you don't have any noise, you should perfectly fit your model. If you cannot even do that, there must be something wrong with the estimation procedure, okay? So here you see my ARE actually is very small, okay? So remember, this is percent. So it's 0.002%, okay? Basically, it's 0. And if I increase the noise to 5% or to 30%, now you see some parameters are much more sensitive to noise than others, right? For example, this one, that's 2,000. This one, 200. So now you can tell that I can actually, most of the time, I can reliably determine the parameter values for these parameters, but not for these two. Okay? As the noise level increase. So,
sensitive rank, how do you calculate the
oh, the rank is just you sort this one ARE, and the first means that's the worst. Okay. So that's one thing we can do. So after we identify, okay, these parameters are the most sensitive one to noise, then the next thing we want to do is that what if we increase the number of time points, and what if we increase the number of replicates, right? Here I just did a simulation based on the real experiment design. See, 3 replicates, 5 time points. Okay. Next, I want to do is that what if I increase the number of time points if I have the resources? What if we have money to get more subjects? Okay, so that's the so-called simulation-based design. What we do is here. So from 5 time points, we increase this to 9. Because for our experiments, at most we can actually sample the subjects each half day, okay? You cannot do more than that. That's why I increased the time points from 5 to 9. 5 is the original design. It's per day, okay? Each day we get an observation. This is actually half day, okay? We have half day observation for this one. Now, the number of replicates, the original design is 3. I increased to 6 to 9, even to 100. I know this number is not reasonable, but it will tell you sometimes even if we increase the number of replicates to some unacceptable number, you will still not be able to reliably determine some parameter values. That's the case here, actually. So even if just look at this one. Even if I look at the have 100 replicates at each time point and I have 9 time points in total, it's still wrong. The RE is still 400%. Okay, which means these 2 parameters are too sensitive, and there's no way you can actually reliably determine them. So whatever I reported, okay, based on this model, we cannot trust the estimate of these 2. This one, and also this one.
But this is still simulation, right?
Yeah, it's simulation. Yeah. So the next step you need to do, either you modify your model structure, okay, or you improve your data quality. So we already showed that if we don't have memory error, you're supposed to get very small RE for all the parameters, right? Even for rho MW. So that's an example of model-based experiment design. And now I want to move on to the so-called semi-mechanistic modeling. It's a little bit challenging. I have to say that at first, okay, because this concept, I cannot say this concept is new, but technically, okay, you will have many problems, okay. Although it does has its advantage, okay, over other type of modeling technique. So, as a modeler, okay, when we publish paper or submit manuscript, one criticism we usually get is that how do you know you already explored all the possible mechanism? Because the reviewer only say the limited number of model structures in your paper, right? You either use the ODE model, develop like 3 or 4 alternative model structures, that's the most, okay? You will not actually publish like the 100 model structures in one paper, okay? People also will question you why you have so many, okay, model structures, because you are not sure about the question or what. So anyway, you get criticisms, okay? Me too. So I also know that only a small portion of model structure we can actually use, okay, to represent our knowledge, right? And in one paper, okay, it's still not possible to explore all type of models and explore all different structures within each type, right? So the so-called semi-mechanistic modeling is sort of a remedy to this kind of problem. And it actually has a strong statistical flavor, okay? So when you have these 3 problems, okay, you probably can consider this so-called semi-mechanistic modeling. The first one is when I model something, okay, I know part of the story, but there is another portion of story I have no idea, because nobody actually did any experiments before, or it's not affordable to do the experiments for this study, okay? So That will be the first reason you may consider this modeling technique. The second one is that I may have undistinguishable parameters. That's also possible. But I don't want to make things too complicated, okay? So let's just say, okay, that's a second scenario, because our focus will be the first one, okay? And third one, sometimes if you like of data, you can also consider this kind of so-called semi-mechanistic modeling, okay? So the basic idea, okay, is that we lump together all the unknown mechanisms into one term. If I don't know, it's fine. I just don't model it, okay? Don't model it in a parametric way. I model it in a non-parametric way. So what I mean is that, remember when we develop a model, okay, within these 2 days, we say the proliferation is exponential, the death is constant. Okay, how do you know this is not exponential and this is not a constant? Okay, so to deal with this kind of problem, what I do is that I don't model in this way. This is a parametric model or mechanistic model. I explicitly specify the mechanism here. The first mechanism here is exponential growth. The second mechanism here is constant death. Okay. Instead of making this kind of explicit assumptions, what I do is that I use a parameter to lump these two together. So now I don't care. Okay, it's a constant or it's exponential, and I just lump them together. Says the change of the cell number per unit time is proportional to this parameter. And this parameter is a function of time. Does that make sense? If I write it in the parametric way, this function of time will be, right? Now I just don't make this assumption. Okay, I just let this parameter to be a function of time. And I will not actually pose any constraints on the shape of this parameter. I will have to let data to tell the shape of this parameter. That's the key. Okay. So now if my parameter looks like this way, then I can numerically integrate this part and then get a pattern for growth of t, right? And now I save the trouble to argue this is the exponential growth, this is a constant. This definitely is a very simple example, but for complicated models, okay, you'll run into this kind of thing because there are some factors you will not be sure, okay? So that's the basic idea of semi-mechanistic modeling, okay? Now mathematically, okay, like I just wrote down, okay, part of parameters, I know what's the exact story. I can just use our mechanistic modeling technique. For example, I wrote down rho tt minus delta because I'm sure that's true. I still can have this parameter, this kind of parameters in the model. For the rest, I just summarize them into a time varying non-parametric parameter. Okay, in the time domain. So that will be the general form of the mathematical formulation. So if one good thing about this is that, let's go back to the example. If my parameter should be a constant, then I will expect to get an estimate of eta like this. Right? Because right now I'm not sure whether it's constant or a function of time. I let the data tell me, okay? If the data tell me your estimate is almost like a flat line, then I can go back, substitute this one with a constant coefficient and fit the model again. You don't want to introduce unnecessary complexity, okay, into the model. And if my estimate says my eta actually should be this way, then I'm doing it right because the data suggests that this mechanism should have this pattern. how we actually use it, the first problem will be identifiability again, okay? So, because I can give you a very simple example. Again, back to the growth and death. If I model my cell growth as a function of time, okay, now I don't need the t here, because once it's a function of time, it can absorb the t term, okay? We used to have rho t, right? Rho is constant, t is actually a function of time. Now if you use a whole term to represent the whole thing, okay, now this is the whole thing, not just the rho, okay? That make sense? You don't want to do this. Okay. If you do this, you get into trouble again. Because t itself is function of time, rho is all unknown function of time. There will be very strong correlation between these two. So you don't want to do this. However, you may think, what if I model my death also as a function of time? So I don't have to worry about the mechanism, whether it's exponential or it's linear. Now you run to the identifiability issue again. Okay, even if your delta is a constant, you still have a identifiability issue, right? This is a arbitrary shape of curve. Doesn't matter if subtract constant or add constant, it can be all absorbed into this term. Does that make sense? For example, if you have a curve, I shift it up, okay, or I shift it down. I can always use another time function to represent what's shifted, right? So that's why, okay, when you use this kind of thing, you still need to verify the identifiability. And unfortunately, it's more difficult to do, okay, than the identifiability analysis we just mentioned before, okay. But there's one simple principle you can consider. You can have at most one time-run parameter in one equation, like I just mentioned. You cannot have two or two more time-run parameter in one equation. And to do the identifiability analysis, the basic idea is that I have x dot equals to f t theta eta t. So although I put something called the differential algebra here, doesn't matter, okay? That's technical terminology. Basic idea is that I want to remove this by doing some, mathematical tricks. By adding different equations or subtract two equations, I want to remove this one. And only left x theta. Let's use the g here, okay. So you generate the equations of x and theta only. Okay, that's the first thing to do. Then you verify whether these constant parameters can be identified or not. Okay, that will be easier thing to do, right? Now, if we verify that all the constant parameters can be identified, then I just solve each time-run parameter. Now it becomes a function of, let's use not S, L, okay, x theta. The second step you want to do is get this kind of solution, okay? So the solution of eta t in terms of x theta, okay? And also you probably have x dot, x double dot, doesn't matter, okay? So now if all my constant parameters are identifiable and my time-run parameter can be expressed in this identifiable constant parameter, then I'm okay. Then I know I can identify this parameter, okay? So that's the basic idea. If you're really interested in this kind of thing, that's a differential algebra. That's something you should look at. And the implicit function theorem, that's something you should look at. Okay. However, basic idea, it's here. So now, after we're done with the identifiability analysis, okay, the next thing is that we want to do parameter estimation. So since we are not posing any constraints on the shape of the time variable parameter, then how we actually estimate it? It can be arbitrary shape, right? And it's infinite dimension, because there are infinite number of points on a curve. So that's why we need to do approximation. So use a linear combination of some basis function, okay? So the so-called basis function is just some pre-specified function form that you can use them to approximate arbitrary shape of curves, okay? You can use them to approximate curves of arbitrary shape. For example, the basis function can look like this, can look like this, can look like this. Okay, this is one of the example of the basis function, okay? And this is actually 3 basis function, okay? B1, B2, B3. That's polynomial, okay? How about that? Just a polynomial. Now, if I use a linear combination of this polynomial, I will be able to approximate any curves of arbitrary shape, because what I need to do is just change the coefficient. Okay. For example, if I change the coefficient of A2 to 1,000, then this one will become extremely high, right? Now the linear combination of these 3 will become this shape, right? I do the same thing to B1. If I change this one, the coefficient of A1, okay, the coefficient right now is A1. Increase it. Now this one goes up. Now, this one. Now the total linear combination of the A1, B1, A2, B2, A3, B3 will actually look like this. See? By doing this, you can create arbitrary shape. Okay? Change the magnitude of each basis function. Okay? You can create arbitrary shape.
Question. So if you had to do these 3 functions, you couldn't just possibly create all shapes. I mean, you're just giving this as an example, right?
Actually, theoretically, I can. Because if you have infinite number of basis functions, you can do anything.
No, that's what I mean. You wouldn't have just 3. You're just giving this as an example.
In practice, you need to do model selection. Okay? So how many bases I needed? For example, I can put 1 to 100, right? However, if my data says I only need 3 bases, then we're fine with 3, right? And you can use model selection like ASA, BSA to select them. That actually can tell you what's the optimal number of basis functions.
Wait, just to repeat, the 3 functions you've drawn there.
That's an example, yes. So, but anyway, now you know by manipulating the magnitude of each basis function, you can create many different shapes, right? And all that shapes actually come from the value of A. Because the BI, they're pre-fixed, pre-specified.
Seems like a reinvention of the Fourier transform or something.
That's just a spline, okay, actually. Or you know, I should not use the word interpretation. Interpolation. Do you know spline? Right, that's actually spline. Okay. So in this way, since I know now we can flexibly create the shape of the curve, then I'm okay to use this approximation, right? I just need to substitute this approximation back to the model. Okay. Now theta is constant. B, there are basis functions which are known. A are constant. So this whole model become a model that with only constant parameters again. So now whatever we developed before, these squares can be applied. Okay? Does that make sense? So, of course, like I said, you need to do model selection. You need to select how many basis functions you want to use. You need to use, or supported by data, okay? You cannot use too much, okay? 100, that's too much. Urine is too much, okay? Urine I can use 3 to 5 will be enough. So, you can use the AIC, BIC, AICC to select them, okay, actually. Because if you use one more basis function, you will have one more unknown parameter, right? Here I have 3 basis functions. I have 3 coefficients. If I use 100 basis function, you will have 100 parameter. So you don't want to use that many parameters, right? You do model selection and select them. So there are some computing issue you need to deal with. However, right now, this kind of modeling technique has been supported in DDiscover, okay? So you can use the spline approximation and do the things I just talked about, okay? So I don't think you can find this kind of thing anywhere else, okay? But anyway, use this kind of thing when you need it, okay? Do not abuse them, okay? You know there are many computing issues, identifiability issues associated with this kind of technique, okay? So now I have 5 minutes. That's good. Because I want to take the time to explain the basic idea of mixed effects ODE model, okay? And that's actually the question I have been asked many times within these 2 days, okay? So the basic question is, if I have a population of or a group of subjects, okay, HIV patients, for example, they are all infected by HIV virus, and so the biologically they're identical. No, I should not say biologically identical. The biological process they undergo, okay, should be similar, right? Which means the mechanism should be the same. The interaction between T cells, CD4 T cells, virus infected T cells. So I can use one model structure to model all of them, right? However, we know there is a variation between subject. So even if I use the same model for all of them, the same model structure, okay, the parameter will be different for each subject. So theta 1 for subject 1, theta 2 for subject 2, theta 3 for subject 3, right? Otherwise, there's no way you can fit a model, right? So the simple thing we can do is that we fit this model to the data of each subject. Does that sound okay to you? Not okay? Okay. If you don't know mixed effect model, that's one thing you can do, okay? However, people have devised this kind of mixed effect model to deal with this problem. Of course, we have some advantage, okay? Otherwise, people will not bother to do that. So one problem with this is that, for example, if in my model, in infection model, I have 5 parameters. Remember? The infection model we used yesterday have 5 parameters. So I have to estimate 5 parameters for subject 1, estimate 5 parameters for subject 2. So if I have 100 subjects, how many parameters I have to estimate? 500. Right? That's okay. Why it's okay? If I have enough data for each subject, that's okay to do. Okay? The problem is, in clinical study, we usually don't. Some patients will drop the visit without any notice. So we're supposed to get 10 data points. We may just get 2. How can you fit 5 parameters from 2 data points. Then what's your option? You have to drop it. Then you lose your information from these 2 data points. You spend money on it, actually, right? Also, you will notice some subjects have extremely large oscillation or fluctuation in their data. Probably most of the subjects have this pattern in the data. However, some subjects totally just randomly jump. Okay, that's not uncommon. Okay, if you look at the clinical data, you have a great chance to get this kind of data. Okay, you just see random oscillation. So how are you going to deal with that? You just throw them away or treat them as outlier?
Most of the time, we throw them away.
This also gives you information about the uncertainty. Okay, from the statistician's perspective of view. Okay, so, and we don't know whether this oscillation is true or just noise. So, since we have this many problems, okay, of fitting the model to each individual data set, that's why people actually devised the so-called mixed effect model. So now, instead of fit this model to each data set, what we do is that we assume theta follow distribution. Now theta is a random variable. You follow distribution, for example, normal, okay, with a mean theta star and also variance, covariance matrix. So now, once I made this assumption, which means we assume all the parameters are correlated. We are assuming that all the subjects are from the same population. That's why they follow one distribution. Okay, although these subjects are independent, but we assume that they are from the same population. That's why you can use one distribution to describe them. Okay, they are independent, but they are from the same distribution. That's just like you draw independent samples from the same distribution. Okay, so now basic idea is that model this parameter as a random variable. So you have a mean and a variance. Okay, so mathematically, I will write the parameter in this way. So for each individual, now we know the mean is this, right? This is the individual parameter. Now we know the mean is this. Now the difference from the mean will be modeled by a random variable, b. Okay? So this is a constant. Or fixed effect. This one is a random variable. This is just like the data model we have, right? And this is called the random effect. Since you have both fixed effect and random effect, that's why people call it a mixed effect model. Okay? So that's the basic idea. And there are many, I know I'm short of time, probably just need 1 minute. There are many packages to fit this kind of model, okay, to your data, okay, in R, in SAS, whatever. And actually, if you go check my webpage, I also have an implementation of some algorithm, okay, to fit this kind of the mixed effect model. Convergence is still a problem. Like the optimization algorithm we talked before, you use a gradient-based method. This also kind of has some, sort of a gradient-based method. You only get trapped by local minima. The algorithm I implement, or the other type of the algorithm, use a sort of global method, but it's slow. Okay, so I have the similar problem. You can use whatever. Okay, depends on whether you can afford. Okay, the computing. So just mention. Okay, if you just use R or whatever SAS, they are all gradient-based method. Okay. Oh, not all. Okay, the default algorithm. Okay, is gradient-based. However, there are some algorithm called SAEM, a stochastic approximation EM algorithm. Okay, that's more like a global although I don't want to say this, okay, SAEM actually is not really a global method, but compared to this one, okay, it has a less probability to be trapped by local minima or whatever. So this is something you can try. There's a package actually in R, okay. You can try. If you cannot get a convergence by using the LME or NLME package in R, this is something you can try, okay. So I guess I will stop here today. And any question? No? So time for dinner. Thank you.